All right. Guess we'll wait for 2 more minutes. How was the homework this week?
I don't know yet.
You don't know yet?
Did we do that bad on the midterm? You had to make it a homework problem?
What?
We did that bad on the midterm? You had to make it a homework problem? No, you should have asked me to release the midterms.
For the first question, the first part of it, that was when I was on the midterm. Is it minus tau times dx?
I mean, second question?
Yeah. Oh yeah, the second question. For the shear force per unit area, I think.
Yeah, that's just the tau.
Oh, okay.
Yeah.
Multiply by dx or just tau?
Yeah, if you multiply by dx, that's shear force per span. Right. So shear force per area is has the same unit as pressure, right? So that's what we usually call tau, and that's basically the viscosity times du dy. Right. That's yeah, viscous forces. Okay, so let's start. So since last lecture, we started working on boundary layers. So today we're going to do a deep dive into boundary layers and analyze the effect of various forces. And today we will particularly focus on the pressure forces. Okay, so although we said that in the boundary layer we have to consider both viscous forces and the pressure forces. And but in terms of separation, flow separation, it turns out that the pressure force plays a major role. And this is what we are going to be focusing on this lecture. And on Wednesday, we will also look at viscous forces. And it turns out the viscous forces plays an auxiliary role in flow separation. Okay, so we will also look at that on Wednesday. So today we'll focus on basically analyzing what are the role of the forces and then focus on the effect of pressure force. So before we do that, we will introduce a few quantities we use to describe a boundary layer. So these are some typical boundary layer profiles. So let me first tell you what these actually mean. Usually when we are describing a boundary layer, we put the y-axis as the direction away from the wall. So this is like the wall. And this is the x-axis. And this is the y-axis. All right. When we are drawing these profiles, what we are really describing is how does the velocity, how does the x velocity, the velocity parallel to the wall, changes as a function of distance to the wall. For example, here I'm looking at a boundary layer that has a obviously different shape from the other boundary layers, right? And in particular, this one actually has a relatively thick boundary where there is a large extent away from the wall whose velocity is not significantly not equal to the velocity away from the wall, right? While this boundary layer is thinner in the sense that you can go slightly away from the wall and the velocity is already very similar to the velocity much further away. Okay, and as we can see from all these profiles, there is usually no discrete changes in velocity, right? That's because any discrete changes in velocity is going to be smoothed out by viscous forces almost immediately. Also, unlike what you are working on in the in either the midterm or the homework, there is no discrete change in the gradient of the velocity either. It turns out any discrete angular shapes in the velocity profile is also going to be smoothed out by viscous forces. not as fast as any discontinuity in velocity itself, but also pretty fast. So usually the resulting velocity profile in a boundary layer is really a smooth function like what you are seeing here. So whatever quantity we use to characterize a boundary layer has to really take into account that the velocity changes very smoothly, right, as a function of the distance from the wall. So that challenge is solved not in a unique way, but in multiple different ways. So there are many different ways we can use to describe the boundary layer. And the three most common ways is actually three different definitions of what is the boundary layer thickness. So let me just introduce these thicknesses. The first thickness is called the delta 99, and it's the easiest to understand. It's also called the 99% thickness. It's the easiest to understand, but actually is the most difficult to really characterize practically, like in complex flows. So what that means is that it is whatever thickness, it is whatever distance away from the wall beyond which the velocity is more than 99% close to the free stream velocity, the velocity away from the wall. It is very well defined if the free stream is uniform, right? So if you have a flow on a flat plate, then we know that only the flow very close to the flat plate has any velocity not equal to the free stream, right? So basically you can characterize it really easily. So for example, if I'm working on the second boundary layer, if this is what I call the edge velocity, UE, that's the velocity on the edge of the boundary layer, then I look at, I'm exaggerating over here, so let's say this is 99%, or let me just call it 0.99 UE. Then I'm going to draw a dashed line down, and wherever it intersects with the velocity profile, right, that height is delta 99, is the 99% boundary layer thickness. Questions on that? Okay, yes?
Is the edge velocity equal to the free stream?
Is the edge velocity equal to the free stream? Yes, for a flat plate. However, if you have an airfoil, let me describe the flow around an airfoil, right? I'm drawing a very fat airfoil, and if the flow comes this way, then the edge velocity, for example, over here is a lot faster than free stream, right? So here, UE is greater than U infinity. For example, close to the stagnation point, on the other hand, right? So let's say this is the stagnation point, this is acceleration. Here, UE is actually less than U infinity. So UE is really the velocity at the wall if you ignore the effect of the boundary layer. All right. Okay, but for flat plate, right, when there is no variation, if the inviscid flow solution is just a uniform, then UE is going to be equal to free stream. Okay, good question. Any other questions? All right. So this is one definition, and the difficulty in exactly defining UE is actually a critical problem in this definition, right? So if you have a inviscid flow solution here, of course you can define UE. But if the boundary layer is finite in thickness, it is not obvious what UE should be, right? So that's actually one of the problems about defining actually not just the 99% thickness, but all different thicknesses. Okay, so the second definition is what we usually call delta star. is the displacement thickness. Okay, what does that mean? The displacement thickness means let me first describe it in mathematics, and then we'll illustrate in this plot why we are defining this particular metric. Okay, so delta star is equal to an integral over y, which is the wall normal direction. Okay, it is 1 over ue, which is the velocity at the edge of the boundary layer, where the integral goes from 0 to, the theoretical definition goes all the way to u infinity. It goes all the way to infinity. In practice, basically, I need to only integrate to outside of the boundary layer because the integrand is ue minus u. So basically, when you are far away from the wall, ue would be equal to u, right? As a result, you don't really have to go to infinity. You only need to go to wherever u is very, very close to ue, right? So basically, the integrand would become 0 when y is far enough away. What does this mean intuitively? So let's focus on one of these plots. Okay, and on one of these plots, so basically the y-axis is y, and the x-axis, if you look at the plot of a profile, the x-axis would be u, right? So here u is equal to 0, here u is equal to ue, and somewhere here u is equal to half of ue. So on this plot, what is ue minus u? ue minus u would be as if you draw a vertical line, and in this vertical line, u would be equal to ue, right? And then the gap between that vertical line and the red profile, that gap is actually u minus ue, right? This gap is ue minus u. That's the gap between ue and the actual velocity in the boundary layer. So what is the integral? Right? You are integrating the distance between the dashed line and the boundary layer profile along the y-axis. So the integral is really the area of this shaded region. Right? Now what I'm doing is I'm dividing that integral by ue itself. So what is this delta star? Delta star can be thought of as the center of mass or center of weight of this shaded region over here. Right? So in this case, we can kind of look at the shape of the shaded region and estimate its center of mass, right? It's basically the y-coordinate weighted, an average of the y-coordinate weighted by how much gap is between ue and u. So we can estimate, for example, maybe delta star is roughly over here. Another way to think about delta star is that, okay, if you draw a horizontal line from delta star all the way to ue and color the rectangle that's bounded between 0 and delta star and between 0 velocity and ue, the area of the shaded region of the yellow region has exactly the same area as the region shaded by black stripes. Right? The area of this yellow region is delta star times ue, right? That is equal to that integral, which is the black striped area. Okay, so what is the significance of this definition? Well, first of all, this definition not only looks at unlike the delta 99, right? The delta 99 only cares about at which height, at which distance the velocity is very close to free stream. It doesn't take into account of exact shape of the profile inside the boundary layer. So, for example, if I know here is delta 99, it doesn't matter if the boundary layer does something like this crazy, or it goes like a straight line, or it curves like that, right? Delta 99 would be always over here. But delta star would actually depend on everywhere how the boundary layer would curve, because that will influence the striped area. Another interesting thing is that this thickness actually has a significant effect from the point of view of conservation of mass. So think about what a streamline would look like if the streamline started from the free stream and ended up somewhere over here. The total amount of mass flow that's sandwiched in between that streamline and the wall would be the same as if the flow is inviscid, but the wall is over here. All right, so the distance between the wall and delta star would be like the effect of thickening the solid body. Right, so if you, instead of having a boundary layer, you make the flow inviscid, but thicken the solid body by delta star, the effect to the free stream would be exactly the same. Okay, so delta star, that's why it's called the displacement thickness. It is a thickness for which you are displacing the flows in the inviscid region. Okay. Okay, so that's the displacement thickness. And the third definition is denoted as theta. That's called the momentum thickness. Okay, the reason it's called the momentum thickness is instead of being significant in the conservation of mass point of view, like the delta star, the momentum thickness is important in the conservation of momentum point of view. So this difference, UE minus U, right? If you multiply a rho onto that integral, this is called the mass flow effect. Okay, so this is basically comparing to the black line, to the black profile, which is an inviscid flow. How much less mass flow is within this boundary layer compared to if there was no boundary layer, right? So basically a rho times this thing is called the mass defect. And if you divide the mass flux defect by rho times UE, that's the displacement thickness. The momentum thickness, instead of looking at the mass flow defect, it looks at the momentum flux defect. All right. And the momentum flux defect turns out to be an integral again from 0 to infinity. And the momentum flux defect is going to be rho times UE, rho times U times UE minus U dy. Okay, so maybe I should write it in a more in a different way. So remember when we were looking at the momentum defect, right? We were first looking at how much mass flux is within a certain d1, right? The mass flux is rho u times d1. And we are looking at if this mass flux was not affected by boundary layer, which means it would have a velocity of ue. That momentum would be rho u dy times ue. right? That's the momentum of that amount of mass flux if there were no boundary layer. But now we have a boundary layer, so the momentum of that amount of mass flux is rho u dy, which is the mass flux, times u instead of times ue, right? So this integral is the difference between a no boundary layer scenario and the boundary layer scenario for the same amount of mass flux. So that's what's called the momentum defect. And to make it the thickness, right? So what's the unit of this? The unit is the unit of density times velocity squared times a distance, right? To make it the unit of distance or thickness, we need to divide this by something that's proportional to rho u squared. And to do that, we just use the most convenient one possible, rho times ue squared. Right? The rho's cancel out, and what we get is just integral. Another way to write it is u over ue times 1 minus u over ue dy. So here everything, all the ratios are non-dimensional except for the uy. So that guarantees that we get a thickness unit. All right. It is a little bit more difficult to visualize what theta is like. So basically, but one thing we can be sure is that if we rewrite this delta a little bit, basically take the 1 over ue into the integral, we get 1 minus u over ue dy, right? And we can compare this integral and this integral, and we can try to guess which one is larger, which one is smaller. Right? Is delta star or theta the larger one? Just look at these two integrals, right? Both are integrating from 0 to infinity, and both contains u over ue, which we know is less or greater than 1. Yes? What? Is theta greater? Why is that? Right, you are multiplying an additional u over ue, which is less than 1, right? So that would make the integrand of this integral to be less than the integrand of this integral at every possible y. And as a result, the integral of the green one would be less than the integral of the black one, right? That means theta is going to be less than delta star. Right? Okay, good. So this is less than delta star. Now, because of this, the ratio of delta star and the theta is actually a very informative non-dimensional quantity that describes the shape of the boundary layer. And if you're going to look at some quantitative calculation a bit later, Mohammed, if you can put some posters on the wall, that'd be great. It turns out that whether the boundary layer is more like this or more like this can be very well described by this shape factor. So now basically the shape factor is a function of the thicknesses, right? So the shape factor H is defined as delta star over theta. And we know it's something that definitely greater than 1, right? It's not obvious, right? But can you just try to guess which boundary layer would have a greater shape factor, which boundary layer would have a smaller shape factor? Okay, the ones all the way to the right has a greater shape factor. Actually, let's actually keep this in mind, right? I'm not going to give you an answer yet, but you're going to be working through an example problem, and that'll give you hopefully some intuition on which shape has a bigger shape factor. Right? It's pretty easy to intuit that the one on the right has a smaller thickness, right? No matter how you define the thickness. And the ones on the left has a higher thickness, but which one has a higher shape factor? By the way, these set of boundary layers are boundary layers under different pressure gradients. Okay, and the ones that are negative has a more adverse pressure gradient. The ones positive has a more favorable pressure gradient. And this is a set of actually when the pressure gradient correlates at a certain power of x, you get you get semi-analytical solutions, what we call like self-similar solutions, and it's a class of solutions called the Falkner scan boundary layer profiles. You don't have to memorize any of these, but we are going to work out some examples of how a boundary layer would respond to pressure gradients if you don't look at if you ignore the viscous forces for now. So let's think about what forces are affecting the boundary layer, right? So the flow is like this, and if you think about, if you trace a streamline, right, that goes with the flow over here, what is du dt? What are the components that affects du dt? Can somebody tell me? Pressure, right? Yes, pressure force affects du dt. And how much? Can you try to tell me what is going to be the pressure force that is going to come into effect over here? So remember, this is a unit of acceleration, right? Meter per second squared. Like, how do you translate the pressure force to, right, something that tells me the acceleration? What is the unit of pressure for? What is the unit of pressure? Yeah, it's force per area, right? Okay, so we know F is equal to ma, right? So the acceleration has to be equal to a force divided by mass. Okay, we know the pressure is force per area, and we are looking at the pressure gradient, right? So if we follow x-axis, which is the direction of the flow, we have dp dx. Actually, of course, it's a minus dp dx because a positive dp dx means deceleration, right? But this guy has a force per area divided by a length again, which is the force per what? Force per volume, right? Okay, how do you get from force per volume to what we want, which is force per mass? Divide by density, exactly, 1 over rho. So that's the effect of pressure force, right? Okay, and then we have viscous forces. Now, viscous force is actually something new. We haven't studied extensively before, right? So we did study how does the viscous force on the wall affects the overall momentum of the boundary layer, but we never actually look at how a viscous force would affect like a particular streamline. So let's think about it a little bit more over here, and then we'll really focus more on the viscous force in the next lecture. So let's imagine a very small stream tube, let's say delta y, okay? That stream tube is affected by viscous forces both on top of the stream tube and on the bottom of the stream tube. And exactly the same as the viscous force on the wall, the viscous force received by this stream tube is proportional to the viscosity mu times the derivative of velocity over here and over here. Okay, so at the top of the stream tube, the velocity further above is faster than the velocity in the tube, right? So the force received by the stream tube should be what? In which direction? Yeah, towards the positive x direction, right? Because the flow above it tries to bring the velocity in the stream tube to the same speed as the flow above it, right? So basically we get a positive viscous force. So that's a mu times du dy, and that's a force. Again, that's a force per area, right? So that's a force per area. Okay, now think about the viscous force over here at the bottom of the stream tube. The effect is opposite, because the flow beneath the bottom is even slower than the flow in the stream tube. So it tries to retard it, tries to slow it down, right? So the viscous force below goes in the opposite direction, and the force is also mu times du dy, but it's a du dy at a slightly different y, right? Okay, so now think about what is the total viscous force. The total viscous force is equal to the mu times du dy above minus mu times du dy below, right? Okay, so if the below and above are spaced by a small delta y, and we use calculus, what is it like? It is going to be equal to the derivative of mu du dy times this small delta y, right? Basically, a small difference between the same quantity but at two different locations, right? It's going to be equal to the derivative of that same quantity times delta y. All right. Okay, so what is the unit of that? Well, the unit of that is force per area. The unit of that is force per area, so this is force per area, right? If you further divide this by delta y, right, because that force actually is proportional to how thick this stream tube is, right? So if you just look at this derivative, it is going to be the force per volume again, right? This is the force per volume, viscous force per volume of flow. It's the same as the pressure gradient. So we get another term that's derivative of mu du dy times another 1 over rho, right? That translates the force per volume to force per mass. That's another acceleration by viscous forces. And of course, when mu is a constant, when the viscosity is a constant, right, which is pretty much the case, unless you have like hypersonic flows where the temperature becomes very different in different layers of the boundary layer, then mu is pretty much a constant even in supersonic conditions before you go to hypersonic. You can move mu out of the derivative and you get the term that is the second derivative of u. Okay, now if you look at a boundary layer profile like this, what is the second derivative of u? Is it positive or negative? Or how does the derivative of u change as you move away from the wall? Right, the derivative of u is pretty much 0 over here, right? How about here? Is it positive or negative? first derivative of u with respect to y? It's positive, right? So the derivative slowly goes from a large positive value to smaller and smaller and smaller to 0 here. So the second derivative, which is the derivative of the slope, is negative, right? So that means viscous forces in this case decelerates the flow. But there are different cases, right? So if you look at a boundary layer like this, it's a little bit different. It's the slope actually is the largest somewhere over here, right? And the slope is actually smaller over here than over here. So there is two regions. In the near wall region, in this boundary layer, the viscous forces actually accelerates the flow, while in the outer regions, the viscous forces decelerate the flow. So we'll remember this when we start to reconsider viscous forces a little bit later. But this lecture will focus on just this term, right? And to see how does this term affects the three different thicknesses as well as the shape factor. Here's the exercise I'll ask you to work on. Okay, so of course it's very difficult to analyze the pressure forces for every velocity at all different y's, right? So let's do an approximation. Let's just think about the u outside the boundary layer is 1 meters per second. Okay, when y is greater than 1 millimeters. Okay, and we just use 3 discrete layers to approximate how the boundary layer look like. So let's say 0.9, very close to the free stream velocity or edge velocity. When we are between 0.6 and 1 millimeters, and 7% of the edge velocity between 0.3 and 0.6 millimeters, and 40% of the edge velocity when y is less than 3.3 millimeters. All right, let's just think about it like that. So can you work out? Oh, I just want to test whether you listened. What is going to be the 99% thickness of the boundary layer? Remember what is the definition of 99% thickness? Yeah, what is the delta 99 in this case? What?
Is it at the edge?
Yes, and what is it? Yes? 1 millimeter, good job, right? So basically, we are essentially thinking about the boundary layer as something like this, right? Okay, so that's kind of the profile. And when I have a UE like that, and 99% UE traces exactly over here, and this is like 1 millimeter, right? So yes, delta 99 is 1 millimeter. Okay, so now the other thicknesses require you to do some calculation. So please start working on it. What is delta star? What is theta? And what is the shape factor? And which one does it look like more? Copy. Yeah, we are considering.
Oh, right. Okay. Okay, yeah, fair.
Theta is 0.53.
Yeah.
And then H is 1.20.
Good. Nice.
Is that what you got?
Yeah.
Let's go, dude.
So now, which one does it look like?
It's gonna be the smaller, like the boundary layer is smaller.
Yeah,
so
it's gonna be
like
more
the
like the
fourth
right one. Yeah. Okay. Good. No.
No.
We have more, right?
No way.
and even more.
We have no more room left in our chalkboard.
Okay.
Let's just write this.
Basically, all the stuff later is the same thing, but just to reverse the pressure gradient. Right now you have. By the way, just to make things easier, so this is square root of 0.9, and this is a square root of 0.8.
All right.
Right, so you already figured out what is the effect of a favorable pressure gradient, right? So let's look at the.
So is that like including like 0 to 50 it accelerates and then 50 to 100 it decelerates again?
Yes. And basically, you're gonna figure out the effect of adverse pressure gradient, and you are gonna see flow separation over here. And let's see what it looks like.
Stop this bitch in yourself.
This constant is included. So
Which one do you think it looks like?
So the first one is going to be 1.06 times
Oh, wait. It's the same as the first one.
Okay, so let me maybe talk about the solution for the last 2 minutes. All right, so I think everybody got number 2. So what happened is that the boundary, as the flow accelerate, okay, which stream tube gets accelerated the most? Which one get accelerated the most? Right? Which layer get the most acceleration from the favorable pressure gradient? Sorry? The one nearest to the wall, right? The one nearest to the wall gets the most acceleration because du dt is equal to u times du dx, right? And that is equal to the effect of the pressure gradient, which is going to be the same for all the stream tubes. And, okay, so that means which one gets the most du dx? Right? For the same right-hand side, would a smaller u or larger u get a larger du dx? Always, like a smaller u gets the larger du dx for the same pressure acceleration, right? So the velocity nearest to the wall gets the most significant effect, as you have seen, and that is going to be the same no matter for adverse or favorable pressure gradient. So what you're going to see if you worked out the 3 is that at 3, the velocity close to the wall almost gets decelerated to 0. All right, if you apply the same difference in the pressure to the velocity at the wall, although the free stream only decelerates, so let's compare between 1 and 3. It decelerated from 1 to 0.94, right? The velocity near the wall decelerates all the way from 0.4 to almost 0. And if you go to number 4, the velocity near the wall would decelerate to beyond the 0. Okay, it would decelerate to a negative speed. And now you think about what the consequence is to the thickness, right? A velocity in the bottommost layer almost equal to 0 means the thickness is going to be very, very high, right? You're doing conservation of mass. A slow velocity means a high thickness. And the velocity negative, which means when the deceleration becomes 0 for the bottommost layer, the thickness of the bottommost layer is going to be infinity, right? That's flow separation. That's where the boundary detaches from the wall and goes to a free shear layer. So you don't have time to work to 4, but if you work out 4, there's no solution to 4. The boundary layer had separated. All right. Okay. So we'll come next lecture and look at a little bit more general principles and then add the effect of viscosity to this simple model. All right. See you on Wednesday.